One of the main things about Leetcode questions is that we think that we constantly have to be doing a lot of Leetcode problems. But in reality, that's not the case. You can take a single Leetcode question and you can actually come up with so many different solutions. So for example, if I take only two sum, right, which is you have a target number that you're trying to get to, and you have this array list of numbers that you have, and you're trying to find the indices of the two numbers that add up to the target. Just from that simple Leetcode question, you can literally come up with so many different ways of approaching the problem and solving it. Not just a simple, okay, here's the map, we're going to store this in a map, and then we're going to find the target minus nums of I and see where those two indices add up to the target. Not just going through the entire for loop, but trying to think of ways that we can make this problem more challenging for our own understanding. Can we create a graph? Can we solve this problem using a graph? Are we able to solve this using a stack, or can we solve this using a cube? Trying to create ways that you can that you can learn so much more from a single question. Because one of the misconceptions is that you have to be doing a lot of these Leetcode questions. You have to constantly be doing Leetcode questions. You have to do many different Leetcode questions, but you can actually extract so many different learnings just from a single question. And the way that you can do that is by trying to think about different data structures you can use. Can I solve this using a particular method? Different ways to solve this, coming up with new innovative solutions to solve this Leetcode question. So we've gone through we went through the two most common ones, but there are other common techniques that you can use. So instead of looping through this twice, running an O of n squared time, and instead of just using a map, what you can do is you can think of this as like a rotation. So you can rotate this. So you can rotate this 842, rotate it again, and then you get 284, and add these up. Can we solve this using some sort of rotation? Are we able to solve this using some math formula? Trying to create new solutions, even to some of the easier problems, will help sort of flex the creativity muscle, and you're able to create more innovative solutions, even from this simple Leetcode question. So that's one of the main learnings, that you don't have to be doing. Yeah, it's good practice to do many different Leetcode questions and a large variety of them, but you want to make sure that you're getting as much information and learning out of even a single Leetcode question as much as possible. And the way to do that is by coming up with these different solutions, and thinking about ways to make the problem even more challenging. Right? So we have this you can we have this Leetcode typical Leetcode question, right? 4283, we want to find two indices. But what if can we do that by doing combinations? Can we do this by doing combination, where we create combinations of two indices, two elements, and add them together? And instead of even doing two, can we do three? Can we do four? Can we do four elements together and see if they add up? Right? Thinking about different variations of the question that you can solve is going to really help you sort of enhance the creativity aspect of the question. So that's the main thing. If we move on to talking about the entire concept of gradient, so we know that gradient refers to the slope of a three-dimensional function, right? In derivatives, is the slope of a 2D function. Gradient refers to whenever we have more than two dimensions, whenever we have five dimensions, four dimensions, and we want to find what's the direction of initial increase, greatest initial increase. You can think of a gradient as that. An analogy you can use as when you're climbing up a hill and you're at any point up that hill, what's the greatest initial increase if you walked in that direction? And that direction is that greatest initial increase. So that's what we refer to as the gradient. So if we have a function, we have this paraboloid function, and we want to look at what's the gradient of this, meaning that at any point along this function, if I were to take a step in that direction, that's the step of greatest initial increase. So you can think of this as like a 3D function, and if I were to take a step in that direction, so in 2x, 2y, which is the gradient of this function, that is the direction of greatest initial increase. And that's what a gradient refers to. And this is the crux of many different machine learning algorithms of optimizing linear regression, finding the solution to linear regression, neural networks, the entire idea of back propagation and back propagating, updating the weights and the biases are all based upon this idea of gradient and finding the gradient of a function. So this is one of the critical ideas that we want to understand. Another idea, and this goes similar to what we talked about when we have even a single Leetcode question, you can make that more challenging and be more creative with it. You could also be more creative with even certain projects. So a couple other projects, right? Even when you're making like a JavaScript web app or HTML or CSS web app, can you make that more challenging? Can you make it more creative? By first, if you're just beginning to learn it, yeah, you learn your basic HTML, CSS, JavaScript by adding the different buttons and making a little summation game or calculator game or making like a prime number checker type of game or something that's something you can do in the beginning. But then can you make it even more fun? Can you add something to it by adding animations? Right? Can you make even like the Leetcode problems that you do, can you convert that into something that's more creative and more fun? So one of the visualizations that you can do is, let's say you have a Leetcode question that you're solving, right? Let's say it's two sum. Can you create some visualization to mimic how the entire algorithm is working? So this again, this is just two sum. If we think about like merge intervals or something, so the entire concept of merge intervals, we look at 1, 4, 5 to 7, and then if we have like some merge, let's say from 1 to 4, and like we have 2 to 7, right? So that 1 to 4 and 2 to 7 should be merged. And one of the common techniques is we loop through this, right? And we see, okay, is this two? Is this two the first element in that list? Is that greater than the last element in the last list, or is that less than the last element in the last list that we saw? So is it less than two? Is it less than four? We know it is, and so that's why we merge them. So, but instead of doing this, can we think of a better way to do this? Can we use some sort of data structure? Can we use some sort of math formula? Can we come up with some pattern that we see in order to do this question a bit differently? So that's how you can sort of create more energy and fun into the types of question that you're solving, not just solving it through the typical way that you used to, but adding more creativity and even changing the problem to sort of make it more fun and challenging. And when we talk about like visualizing the algorithm, so the entire idea of like looping through this entire list and then seeing if this element is less than this element and then merging it, you can visualize that. Right? So can you create a JavaScript app that can do these visualizations of these algorithms? And you can do that by learning animations and then creating more ways to sort of make the projects creative, adding more things, adding more features, are you able to, even some of the concepts that you may be learning, are you able to create some sort of animation or visualization attached to it that will sort of make the learning experience better because you'll be able to actually do something with it, and you're able to make even a creative project with that learning. Right? So it's not just about, okay, we made this project, we're done, but are we able to sort of add another piece of creative element to it by sort of taking what are the things that we've already learned, let's say a Leetcode question or something we've learned in class, and can we apply it and can we convert that and make it more creative by doing these creative projects that extend upon whatever we've already made? So those are some of the lessons. If we talk about, moving on to different algorithms. So if we go to like statistical significance testing, right? Statistical significance testing. Whole purpose why we have this is because whenever we're referring to groups of populations, or whenever we want to compare means between two different groups, proportions between two different groups, we know that, hey, just measuring the sheer proportion or the sheer mean is not enough. We need some sort of way to be able to decide if these two numbers or these two proportions, these two means are statistically significantly different. They could be different just by chance, right? If I flipped like 1,000 coins and let's say we landed on 586 were heads, is that enough to say that the coin was unfair? We don't know. We need to perform a z-test. We need to perform some sort of statistical test to and create our known alternate hypothesis that we can use to determine if this is such a skewed result that it deems us to conclude that the coin is unfair. So we need some sort of process in order to compare these two different means, two different proportions. So that's why we have statistical significance testing in the first place. is that can we come up with a way? Are we able to come up with an algorithm? Can we apply an existing algorithm like z-test or chi-square test for expected counts and see if proportions are statistically different, if the means are statistically different, if the two groups are statistically different, and we're able to do that when we have statistical significance testing. So that's the importance of it whenever we're doing conducting a study, even in when we're comparing raw counts or even raw proportions. A lot of times what we do is we just say, okay, like 66%, that naturally seems higher than 60% without taking any consideration into what the sample size was, without taking into any consideration of what the other categories possibly were, what the expected counts are, without doing any distribution testing, without looking at any significance testing. We just sort of almost, without looking at any of that information, conclude that these two proportions are different. But we know that using statistical significance testing will help us to create more fundamental, more sound judgments when we compare different groups. It's going to help us visualize and think about comparing these groups a lot easier and a lot better. And it's going to overall make our processes and testing a lot more sound and reasonable and credible. That's the entire importance of statistical significance testing. And then a couple other things. So we look at clustering in general. The reason why clustering is so important, the reason why unsupervised learning is so important, is because there's going to be times where we don't have labeled data. There's going to be times where we're given this data, but we don't exactly know what we are trying to predict. We don't have something to try to predict. We want to find some sort of patterns or trends in the data that allow us to get insights, whether it's customer segmentation, whether it's through, are we able to find some sort of pattern or trend that allows us to categorize different groups of people, categorize different items, maybe even categorize different tweets? Are we able to find some pattern or characteristic even when we don't know what it is that we're trying to predict? Or even when we don't know what we're trying to predict, are we able to find some characteristics or patterns? And that's the entire purpose of unsupervised learning of these clustering algorithms. There's many out there, DB-scan, hierarchical clustering. PCA is more of a dimensional value reduction algorithm for visualization, but even PCA, the k-means is common. If you want to cluster like different documents, you can also use TF-IDF, and then there's a lot of different techniques for clustering these different texts as well. So that's the importance of clustering. When we look at some of our common machine learning algorithms like linear regression and SVM and random forest, we see that all of them have different parameters. Some control bias, some control variance, some are used in many different settings. Linear regression more often used when we're trying to predict a continuous variable, logistic classification, so they're used in different settings. But the one thing that they all have is this notion of addressing bias and variance. So we know that bias is an underfitting condition, and then variance is an overfitting condition. We know that bias, when we have a high bias, that relates to high underfitting, which means our data is able to generally capture the long-term trends, but it's overly general. It's too general. It's not able to capture some of the even the important specific details of our data set, of our training data set. It's not able to learn the intricacies and nuances of the training and of the data. So that's what underfitting refers to. So an example that you can think about is if we have this, say, data, it generally follows, let's say, this quadratic distribution, right? And then we fit it with like some linear regression line. Like, yeah, over the long term, it might produce somewhat accurate results, but we can see that it generally doesn't capture the systematic nature of this data, which is sort of a quadratic relationship. And so that's the entire idea of having a high bias, is we have this high underfitting. Where yes, we might be able to sort of capture the long-term relationships, but it's overly general. We're not able to capture a lot of the specific details and nuances of the training environment. And when we have high variance, that means we're not able to generalize to new data points. Our model is too sort of captures a lot of the specific details of the training set. So if we have a high variance, it may lead to something like if we have like this, if we have this, like these data points, and our model is like something like this. Like it too closely captures even the noise in the data set. So it might capture some noise, it might capture noise. It's unable to generalize to new unseen data points, unable to generalize. So that's one of the fundamental questions, and really all of machine learning is how can we have this balance between bias and variance? How can we make sure that our model is generalizable to new unseen data points, but also captures the systematic relationships within the data that we're looking at. So that's one of the main ideas of machine learning that we're trying to always answer whenever we're implementing any model is how are we able to achieve this balance. So that's what I wanted to talk about. And we went over some significance testing, went over how to sort of be more creative with our approach, of our problem solving approach, making problems more complex, more challenging for us to actually solve, how much we can extract even from a single question, even from a single Leetcode question. We can extract so much information. We can learn so much by adopting to playing around with these different approaches, creating different versions of the problem, making it more challenging. Because as we mentioned before, one of the misconceptions is that you have to be doing many varieties of these Leetcode questions, which it's true. Yeah, you have to progressively increase the difficulty, but you could also increase the difficulty by increasing the difficulty even of the easier problems as well. But then we moved on to talking more about gradient. We know that gradient is the direction of greatest initial increase. We talked about the importance of applying that creativity to even your side projects in JavaScript, HTML, CSS projects, adding certain animations. Are you able to even visualize what the algorithm is doing through through a cool animation in JavaScript? We talked about significance testing, the entire idea being that instead of just comparing the raw proportions or the raw means, can we compare using statistical significance testing as well? So that's going to provide more validity and make our results and findings a lot more sound and reasonable. And then finally, we talked about linear regression and bias variance trade-off. So that's it for this video. I'll see you next week.